In our last video, we looked at general linear first-order differential equations, and we were able to solve them either by direct integration or by using the integrating factor. In this video, we're going to drop the condition that it needs to be linear, and we will look at nonlinear first-order differential equations. The general form of our first-order differential equations is m of xy plus n of xy dy dx equals 0. And this general form, if it's nonlinear, and again, nonlinear means y can now be raised to a power like y to the third, or maybe it's a variable of sign, so it's sine of y, or maybe some other number is raised to the y, like e to the y. So now f can be nonlinear, but when it's nonlinear, and in this form, there's no universally applicable method for solving this equation. However, if mxy is only dependent on x, so we can write it as mx, and nxy is only dependent on y, so we can write it as ny, then this form can be solved. And that is what we will be doing in this video. And the steps we will be doing is first putting our equation in this form, mx plus ny dy dx equals 0. We separate the x and y variables. Often that means we just move the mx over to the other side of the equation. So sometimes I actually don't do this. But I identify my mx and I identify my ny, and then I separate my x and y variables, and then we integrate regarding y as a function of x. And this is an example we will be going through. Our first example is to show that dy dx is equal to x squared over 1 minus y squared is separable, and find its integral curves. Following the three steps here, first I want to put it in mx plus ny dy dx equals 0 form. So I am going to move this 1 minus y squared to put it with the dy dx. So essentially I'm putting all the y's together, and then my mx. Again, my ny, I want to only depend on y, even though y is a function of x, and my mx is only a function of x. So now I have my 1 minus y squared of x times dy dx, and then I'm going to move my x squared over, so I have minus x squared equals 0. So again, here is my mx. It's only, this is only a function of x, and here I have my ny times dy dx. And my ny is only dependent on y, even though y is a function of x. So now I'm going to separate my x and y variables, so maybe it was a waste of time moving it over, but I did want to put it strictly in this form just to show you. But I have my 1 minus y squared x dy dx is equal to x squared. And then I'm going to integrate both sides with respect to x, and I'm going to keep in mind that y is a function of x. So many textbooks will just write your y here. I often like to put the y of x just to keep reminding myself. So anyway, here I've integrated both sides of the equation with respect to x. So here I have my y of x, my 1 integrates to y of x, my y squared x integrates to minus 1/3 y cubed of x. And it's important to remember when you integrate this with respect to x, the y of x becomes 1, but you have to use the chain rule, so you have to multiply by dy dx, which is what you have here, the 1, and then this dy dx outside the parentheses multiplies the 1. And then this part here integrates to minus y squared of x, but again, because of the chain rule, you have to multiply by dy dx, which again is this dy dx out here, which multiplies by your y squared. Anyway, so that's this side of the equation. On the right-hand side, you have 1/3 x plus c. Oh, I'm sorry, that should be 1/3 x cubed plus c. Multiplying everything by 3, I get 3y of x minus y cubed of x is equal to x to the third plus c, and I can just rewrite that moving the x cubed over minus x cubed plus 3y of x minus y cubed of x is equal to c. If I want to solve this in general, for the general mx plus ny dy dx equals 0, I can let h1 of x be the antiderivative of m of x. That is, h1 prime of x will equal to m of x. I can let h2 of y be the antiderivative of n of y. That is, h2 prime of y is equal to n of y. So then my formula, m of x plus ny dy dx, my original equation, can be rewritten as h1 prime of x plus h2 prime of y dy dx equals 0. Now, regarding y as a function of x, when I take the derivative of x of h2 of y, I'm going to get h2 of y dy dx, which is equal to d dy of h2, the derivative of h2, times dy dx. So this d dy of h2 is just the rewritten form of h prime of y. It's just the derivative with respect to y of h2. And I should also just re-emphasize the d dx h2 of y to this here, h2 prime of y dy dx. This is the chain rule, so you have to add the dy dx at the end, which gives us that h1 prime of x, h2 prime of y dy dx. Again, that was our original mx plus ny dy dx rewritten in terms of h1 and h2. So now this formula here, or this equation here, becomes d dx of h1 of x, since h1 prime is just the derivative of h1 with respect to x. And this here, the d dx of h2 we just saw was equal to h2 of y prime dy dx. So I can substitute this in, and this equation becomes this equation here. I feel like this is a lot of manipulating the dy dx's, which is a lot. But it's, if you really look at it, you can see what's going on. So now I can integrate both sides of this equation with respect to x. Now the h1 prime of x and h2 prime of x by this equation here is equal to 0. So the integral is going to be equal to the integral of 0 dx, which is just some constant. On this side here, I have the integral of a derivative, which is just simply whatever is inside. So again, the integral of the derivative of these two, of this sum, is just equal to this sum. So now I have c is equal to h1x plus h2y. And this is the implicit general solution. That is, c is equal to whatever mx's antiderivative plus ny's antiderivative. And you also know from the fundamental theorem of calculus, because h1 is the antiderivative of m, that h1 of x minus h1 of x naught is just the integral from x naught to x of ms ds. Again, the s is just a variable of integration. Similarly for h2, since h2 is the antiderivative of n, h2 of y minus h2 of y naught is equal to the integral from y naught to y, n of s ds. So here is our final implicit solution to the initial value problem, which is the integral from x naught to x, m of s ds, plus integral from y naught to y, n s ds. And so the point of working this out is to show that you can solve this type of equation using this the integration, this antiderivative, but the point is not so much to memorize what the solution looks like, but to just have a way of working, know that you can solve it, and then we'll have that method of working it out. For example, we'll do another solve dy dx is equal to 3x squared plus 4x plus 2 all over 2 times y minus 1, with y0 equals negative 1. And we also want to determine the interval which the derivative exists. And now just looking at this, we start out, I'm going to move this 2y minus 1 to the other side of the equation. And I did write my y now as a function of x, just to emphasize that. So I have 2y minus 1 dy dx is equal to 3x squared plus 4x plus 2. So here you can see you have your function m of x. Here you have your function n of y. So I have this in the form where I can identify my m and my n, and then I separate my x and y variables. On one side are my y variables. Here are my x variables, and then I integrate, remembering to regard y as a function of x, which is why I put this y of x. So I integrate both sides of the equation with respect to x. And when I integrate, I'm going to get y squared of x minus 2y of x. Just to note, to double check this, when I take the derivative with respect to x of y squared of x minus 2y, here I'm going to get 2y of x, but I have to remember to use the chain rule. Since y is a function of x, I have to multiply by dy dx. And then I have the derivative of minus 2y. That will just give me minus 2, but again, I have to multiply by dy dx because of the chain rule. So this here is exactly what is inside the integral. So I know I've done my integration correctly. And over here I have x cubed, this goes to 2x squared, and this is 2x plus c. So this is my general solution. For my initial condition, y of 0 equals negative 1, that is x equals 0, y equals negative 1, when I plug that into this equation, on this side when I have x equals 0, I just get c on this side. Over here on this side I have negative 1 squared, which is positive 1, minus, except then you multiply by a negative 1, so plus 2 is equal to 3. So I get c is equal to 3. So my final solution for my initial value problem is y squared x minus 2y of x is equal to x cubed plus 2x squared plus 2x plus 3. And I also noted this was an implicit solution. In other words, we haven't solved implicitly for y, but if we have some function y of x, just say phi of x, that satisfies these conditions, then we would say that this phi of x, is equal to a solution to this differential equation. But actually, in this case, often it isn't the case that it's not easy to do. But in this case, we really can make an explicit solution for x. So we're going to solve for y in terms of x. So I have my y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus 3. So I can add 1 to both sides, which will allow me to complete the square. And on this side, I'll have y minus 1 squared. And here I add the 1, so I get x cubed plus 2x squared plus 2x plus 4. So when I take the square root, I get the plus or minus the square root of this polynomial. And then I can add 1 to both sides, and I finally get y is equal to 1 plus or minus square root of x cubed plus 2x squared plus 2x plus 4. And it turns out only the negative square root here satisfies the initial value problem. So this is an explicit solution to this differential equation. And then I also have this last question, determine the interval in which the derivative exists. So looking back up here, actually looking over here, we'll have a problem when this here is not real. So we need this polynomial to be greater than 0. And setting it equal to 0, we see it crosses the axis at x equals minus 2. So what we want is for x to be greater than negative 2. And again, just to repeat, in this example, it was not difficult to solve explicitly for y as a function of x. However, this situation is exceptional. And in general, we will often it'll be better to leave the solution in implicit form here. So another example, dy dx is equal to 4x minus x cubed over 4 minus y cubed. We want to draw the graphs of several integral curves and find the solution passing through the point 0, 1 and determine its interval of validity. Again, moving the 4 plus y cubed, multiplying both sides of the equation, we have 4 plus y cubed dy dx is equal to 4x minus x cubed. So here we have our mx, here we have our ny. We're going to, and they are separate on different sides. Our x's and our y's are separate on different sides of the equation, so we're going to integrate. So here I integrate both sides of the equation with respect to x. And here I get 4y, and then plus 1/4 y to the 4th. And I can note that if I take the derivative of this, I do get what's inside the integral. And then on this side, I get 2x squared minus 1/4 x to the 4th plus c. So just to get rid of the 1/4, I multiplied everything by 4, and I get y to the 4th plus 16y plus, moving this stuff over, x to the fourth minus 8x squared is equal to c. And this is my general implicit solution. My solution through the point 0, 1, so I plug in x equals 0, y equals 1. So here I have x equals 0, y equals 1 will give me 1 plus 16 is equal to c. So my solution to the initial value problem is y to the fourth plus 16y plus x to the fourth minus 8x squared is equal to 17. The interval of validity, well, it's valid as long as the function is differentiable. The problem is when we have 4 plus y cubed is equal to 0, where the denominator is 0, and that's at x equals plus or minus 3.48, and y is equal to minus 1.5874. There are 3 notes that I wanted to go through. First, sometimes a differential equation of the form dy dx equals f of xy has a constant solution, y equals y naught, and such a solution is usually easy to find because of f of xy is equal to 0 for some value of y naught. So for example, here, if you have dy dx is equal to y minus 3 cosine x over 1 plus 2y squared, here we're looking at, here we have dy dx is equal to f of xy. At y equals 3, we can see that this goes to 0, so this whole term goes to 0. So the constant solution, y equals 0, is an easy solution to find. But you can find others once you do the technique here of separating the variables and integrating. Second, sometimes investigation of a first-order nonlinear differential equations can be facilitated by regarding both x and y as a function of a third variable t, so that dy dx becomes dy dt over dx dt. And then when you look at dy dx is equal to f of x over g of y, then you have dx dt is equal to g of t, and dy dt is equal to f of x y. Kind of the dt's sort of cancel out. And last, and we've mentioned this before, in the second example, it was not difficult to solve explicitly for y. However, sometimes you will leave the solution, and actually most of the time, you will leave the solution in implicit form, which we have done most of the time. And the last thing I wanted to do was to compare again that what we just did for separable equations was for general first-order equations versus what we did in our last video, which was for linear first-order equations. So again, the form here, you can see that dy dx can be multiplied by a function of y, but this function of y does not need to be linear. Whereas here, our function of y is linear. That is one of the requirements. So for the examples, and both of these are for first order, both of them just have one dy dx. There are no d2 or second order derivatives. And then we have this form here and this form here. So just comparing the two example problems we have, so looking at this here, because of this y is not linear, it's a cubic, not a linear relation, right away we're not going to be using this method of integrating factors. We're going to be using the separable equations. Versus here, when we look, we have exactly the form of y being linear and exactly this form here. Once we divide by t, the whole equation by t, we have this exact form. So here we would try the method of integrating factors. Okay, so in this video, we talked about general first-order differential equations. They no longer have to be linear, but if they're nonlinear, there's no universally applicable method of solving the equation. So we looked at the special case when m is only dependent on x and n is only dependent on y. So we have this form, in which case we can solve it. We did that by separating the x and y variables, and then we integrated regarding y as a function of x. And that's it for this video. Thank you for watching.